Hello everyone, welcome to our 7th lecture of our Introduction to CFD course. This time around we're going to be working with a new type of problem, because it's a problem that involves electricity to generate heat. We're going to work with the flow through a heating coil, right? So what's gonna happen is gonna have this blue ring right here where water is gonna come through and is going to be heated by this red coil right here. Okay, so this is basically a very simple heating system, but you can also envision this as a cooling system, right? For example, in nuclear stations we use water to cool off the process that is happening in the nuclear power plants. Okay, so this is a very analogous system that could be used as well for cooling instead of heating. All right, so in this case it's gonna be a heating problem, but you can also envision this as a cooling system. All right, instead of you heating up the water, you are also cooling the coil. All right, this is also can be something that you see in computers, right? You have very sophisticated cooling systems that are inside our computers nowadays. All right, especially supercomputers. Well, so what is the purpose of this tutorial? This tutorial demonstrates the capabilities of CFD to model conjugate heat, as well as we're gonna have differences in conductivity between the extremities of our coil. Okay, so there's gonna be a fluid domain for the water. We're also gonna have a solid domain for the coil. And the fluid domain, like I said, is gonna be this ring region that will envelop the coil, and it has water at an initial temperature of, I believe, 300 Kelvin, flowing through it at 0.4 meters per second. The copper coil is going to have a 4.4 volts difference in electric potential from one end to the other end, and is given an initial temperature of 550 Kelvin. All right, so it's 250 Kelvin hotter than the water. All right, so we're going to assume that the copper has a uniform electric conductivity of almost 60 times 10 Siemens per meter. All right, and there is a 1 millimeter thick calcium carbonate deposit on the heating coil. The material parameters that we're going to use for this calcium carbonate deposits are going to be 100.87 kilograms per kilomole, sorry, for the molar mass, 2.71 grams per centimeter cubic for density, 0.9 joules per gram Kelvin for specific heat capacity, and 3.85 watts per meter Kelvin for the thermal conductivity. Okay, so these are our introduction values. Don't worry, when we are inserting the boundary conditions, I'm going to say these values again. But as of right now, let's begin our tutorial. So let's open CFX. Wow, today it opened really fast. That's great. Let's change our heating directory, our working directory for this one, heat transfer from a heating coil, which is going to be the one that I'm going to send you. And let's start CFX pre. All right. There you go. Now let's create a new file, general, and let's already save it. All right, I'm gonna name it heating coil. It's not voil, coil. There we go. Now I hope you guys already know the initial steps at least, which what we need to do here, we need to import the mesh. So because our working directory is set appropriately, we are going to be already in the correct folder. So let's open heating coil mesh.gtm. There we go. We can see our ring where the water is gonna come through, and our heating coil right here, spiraling through the ring, right? Let's do this. What I did was right click, predefined camera, isometric view, Z up, all right? So what we're gonna do first is we're gonna do some editing in the materials. We're gonna edit the copper material that is already present in our system. So we're going to expand materials. We're going to right click copper and select edit. Okay. What we're going to do here is in material properties, we're going to expand some stuff because we're going to be working with electrical properties. All right. So what we're going to do here is let's expand electromagnetic properties, and let's also expand let's also check electrical conductivity, okay? And our electrical conductivity is gonna be, like I said, nearly 60. The proper value is 59.6 times 10 to the 6. And for those of you that don't know, this S right here is not seconds, all right? This S is Siemens. Think of Siemens as the opposite of ohm. Remember, ohm was the electrical resistance. It was the measure of how difficult it was for electricity to go through the material. Siemens is the opposite. It's how easy it is for the electricity to go through the material. Okay? So this is the thing that we need to edit in the copper material. We can click apply and then OK. Now we're going to create the calcium carbonate deposit that we're going to have in our system. Okay, so right click materials, insert material, and we're going to name it calcium carbonate. Okay, it's carbonate, not carbonate, calcium carbonate. Okay. So the material group is, we're gonna let it user. The thermodynamic state we're gonna change because this is not going to be a liquid. This is gonna be a solid. Okay. Now let's go to material properties. The thermodynamic thermodynamic properties we're going to be working with is molar mass and density. The molar mass will be 100.087 kilograms per kilomole. All right. The density will be 2.71, but it's going to be 2.71 grams per centimeter cubic. Okay. Make sure you pay attention to the unit. All right. Now let's check specific heat capacity, and the value for this is going to be 0.9 joules per grams Kelvin. Okay, not kilograms, grams. Make sure again you are paying attention to the unit. Now let's go to the thermal conductivity. Okay, what thermal conductivity is going to be in transport properties. Okay, check thermal conductivity, and the thermal conductivity value is going to be 3.85 watts per meter Kelvin. Okay, so make sure you have these properties properly set up. Click apply and click OK. Now we're going to create the domains. Remember I said we will have two domains, one fluid for the water and one solid for the heating coil. So now let's create the water domain. So we're going to click here in domain and we're going to name it water zone. Okay, the location is going to be the annulus, which is the same as ring right here. The material will be water. The reference pressure you can leave 1 atm. Go to the fluid models tab, and now as you can tell, because this is a heating problem, we will need to set up a proper heat transfer model. So we're going to use the thermal energy heating model. Okay, next initialization, you can go here and check domain initialization and leave the rest as it is. Okay, click apply, click OK. Now we will create our solid domain, which we will name solid zone. Okay, so the characteristics for the solid zone will be: the location is going to be the coil, which is the twisted pipe. The material will be, I'm sorry, not the material, the domain type, like I said, is not going to be a fluid domain anymore. It will be a solid domain. The material will be copper. Okay, now make sure that the heat transfer is set to thermal energy as well. We will work with electricity, so we need an electromagnetic model that will be the electric potential model. Okay, like I said in the previous lecture, if you want to get into the theory behind these models, all you need to do is press F1 here, and we will open the contextual help that will guide you through the theory of this model. Okay, now go to initialization. The domain initialization will already be checked, and change the temperature option to automatic with value, because we know the temperature of the ring, of the coil, and it will be 550 Kelvin. Okay, so click apply, click OK, and you can already see that we have our water zone, our solid zone, and we have the interface that is the region where the fluid zone is touching the solid zone. Okay, now we will create our boundary conditions. Because we have two domains, if you just click here in boundary, nothing's gonna happen. Okay, you need to click in this in this red arrow, and it will ask you, okay, you want to create a boundary condition, but which domain do you want this boundary condition to be created in? Okay, first we're going to create the boundary conditions in the solid zone. So select solid zone. The name we will name ground, which will represent the region where it has 0 volts in our heating coil. So the region is going to be coil and 1, and it's going to be that one right there. Okay, so make sure that the boundary type is set to all, the location is coil and 1, and now let's change some boundary details. Okay, change from the electric field from 0 flux to voltage, and set the voltage to 0 volts. Okay, click apply, click OK. Now let's create the other end of our coil, which we'll name it hot. Okay, the only difference here is going to be the location, which is going to be coil N2, and of course the voltage. We go to boundary details, we change here from 0 flux to voltage, and the voltage here will be 4.4 volts, which will create a difference in electric conductivity, which is going to create heat transfer. All right, so click apply and click OK. Now we will create the boundary conditions for the water zone. We will name this inflow. So as you can already imagine, it's going to be the boundary conditions that is going to be the inlet for the water, okay? Because you already named it inflow, the proper location is already set, which is going to be the bottom ring face, okay? Go to boundary details. The normal speed of water is 0.4 meters per second, and the temperature is 300 Kelvin. Okay, now we will create the other end of our water zone boundary condition, and we will name it actually first, because we will need some expressions. We're going to create some expressions first for this boundary condition. This boundary that we will be working here is not going to be an outlet, it's going to be an opening boundary condition, because for this case it's appropriate for the axis to be an opening boundary condition, because at some stage during the solution the coiled heating element will cause some recirculation at the exit. So at an opening boundary condition we were going to set up a temperature for the fluid that enters through the boundary. Okay, so in this case it's useful to base this temperature of the fluid on the fluid temperature at the outlet. So since you expect the fluid to be flowing mostly out through this opening, okay, so let's create some some expression, sorry. So right click expression, insert expression, and the name for this expression is going to be outlet temperature. Okay. How the temperature expression, the expression for the outlet temperature is going to be this one. Okay, so it's going to be area average, open parenthesis T, which is the default variable for temperature, close parenthesis, at outlet flow. Okay, I already inserted the expression here, but I want you guys to try to put this expression like we did in our previous lecture, which was like you're going to right click it and you're going to look for the locator based area average, and then you're gonna type T. Okay, I want you guys to try to do this on your own. Okay, if you are having trouble, you can go back to our previous lectures where we set up expressions very similar to this one. Okay, so click apply, and now we can close the expressions tab and let's create our opening boundary condition, which we're going to name it outflow. The outflow is already selected here, which is the upper ring face, but like I said before, we're going to work with an opening boundary type. Okay, so go to boundary details. The relative pressure that we will work is going to be 0 Pascal. The opening temperature is going to be the expression that we just created. Okay, so click here, enter expression, and type outlet temperature. Click apply, click OK, click OK, and you can see the blue rings coming in and out of the ring that express the opening boundary condition. Okay, now we're going to do a little editing in our interfaces. Okay, I already told you that this was already created when we created the two domains. Okay, so we're going to do our own interface instead of using the default one. Okay, so click here, which is domain interface. We can use these names, there's no problem. The interface type is going to be fluid solid, because we have a solid domain and a fluid domain. The first domain is going to be the water zone, and is going to be the coil surface. Okay, So this is basically the outer wall of the ring, and the software itself will already select the other region that is in contact with this one, okay? Which is going to be the inner wall of the heating coil, okay? Now go to additional interface models, check heat transfer, and change here the interface model to thin material and select the calcium carbonate, okay? The thickness of the calcium carbonate is gonna be 1 millimeter, all right? Make sure you change the unit, okay? Click apply and then click OK. Now let's set up our solver conditions. So click here in solver control. The only thing that we're going to change here is the time scale. We're not going to use an auto time scale. We're going to use a physical time scale of 2 seconds. Okay? Click apply and click OK. Now let's run our simulation. So let's click here. We're going to save the DEF file as heating coil, and we're going to run it. So let's start the run. What I want you guys to send me here is this windows right here. You can see that we have the energy for the thermal energy here, but also we have this new tab, the electromagnetism tab, that we didn't have in our previous simulations because we were not working with electricity. Okay, so what I want you guys to send me is the converged state for the RMS mass and momentum, and also the electromagnetism, okay, for the electric potential. All right, the convergence criteria for our residual targets are 10 to the minus 4. So when all the lines cross this one, cross the 10 to the minus 4 line, we'll have a converged simulation, okay? And you can see the heat transfer and the turbulence aspect. Hold on a minute, I think my dog wants to be let out of the room. And there she goes. Sorry for that. The simulation is still going through. As you can see, the simulation takes a bit longer because we are dealing with not only the hydrodynamic processes, but we are dealing with, we are using a thermal model, and we're also using electricity. So this is gonna change, this is gonna make the simulation take longer. Okay, this is normal, all right? Don't think that you did something wrong because your simulation is taking too long, all right? And now I want you guys to send me this image with the RMS residuals, and I want you guys to send me the electromagnetism image, all right? The electromagnetism tab, okay? Now let's process our results, shut down the CFX Solver Manager, and now let's take a look at some stuff. Now, because we have two domains, make sure that both of them are selected to be loaded, all right? I want you guys to see both of them. We're not gonna work only with solid domain nor the water zone, all right? We will work with both of them. And there they are. Let's predefine camera isometric view Z up, and so we can better see the heating coil, let's change our wireframe, okay? From 30-degree angle to a 15-degree angle. There we go. Now we can better see the heating coil, all right? Now let's check the effect of the calcium carbonate deposit and see how it affects temperature, okay? So what we will do here is we're going to create a contour plot right here. You can leave it contour 1. The location will be domain interface side 1. The variable will be temperature, and the range will be local. Before we discuss this, let's change our legend. Instead of using the scientific notation, we will use the general one. So double click legend, go to appearance, and change from scientific to fixed. And as you can see, the temperature in this side of the heating coil ranges from 376 to 824. All right, now let's change the location. Instead of side 1, let's use side 2. And you can see that the temperature range has elevated. All right, it was the lower boundary was 376. Now it's 421 Kelvin, and the upper boundary was, I believe, 824. Now is 959. So you can imagine which side of the heating coil is the inner side and which one is the outer side. The outer side is the side 1, right? Because the outer side it has the lowest temperatures. So we can imagine that this is the side that is in direct contact with the cold water. Okay, so this is the outer wall and this is the inner wall. Okay, so I want you guys to send me these two pictures right here. The one for the outer wall, remember, go to save picture, all that stuff, 500 scale for a better quality. And I want you guys to send me the one for the inner wall, okay? So I hope you guys understood that just basically by looking at the temperatures, we can already tell, okay, this one is the inner wall that is not in direct contact with the cold water, and this is the outer wall because it has the lowest temperatures, and therefore we can assume that it's in direct contact with the cold water. Okay? So now let's create a locator. We're going to create a cylindrical sheet that is going to run through the system and is going to give us a very clear temperature distribution both in the water and in the heating coil. All right, for this we're going to create an expression. So go to the expressions tab. You can click anywhere. You can right click anywhere here and select new, and the expression is going to be exp radius. All right, the expression is going to be this one, which is basically going to give us a radius. All right, again, I want you guys, you're gonna need to type this expression here, and you can do it directly. All right, you don't need to do right click, variables. Actually, you can do this, but it's much faster if you type this because these are default CFX post variables. All right, now that we have already created an expression, we're going to create a variable. And how we do this, you can just go here, click variable, and we're gonna name this variable radius. All right, the method is gonna be that we use to create this variable is gonna be the expression method, but the expression we need to select is the one that we just created, which is right here, right? exp radius. Okay, so click apply, and let's go back to the outlet to the outline 3-bar. Okay, now go to location, and we're going to create an ISO surface, which is a surface that has the same values all around it. Okay, the name can be ISO surface 1, that's okay. The geometry that we use will be the variable that we're going to use will be temperature, and we're going to select a value of, sorry, the variable is going to be radius, this is the one that we just created, and the radius will be 0.8 meters, okay? Now the color scheme is where we're going to change the variable to temperature, okay? And the range will be, I would use a user specified one, but a local one, but if you leave a local one, there are going to be extreme values of temperatures that happen in very, very small regions of this ring. So to better see, let's use a user specified one, and the minimum value we use 299 Kelvin, and the maximum value we will use 309 Kelvin. Okay, now let's click apply. And to better see this, let's uncheck contour. So there you go. You can clearly see that before the water reaches the heating coil, it has the lowest value of temperature of 299 Kelvin. But as soon as it hits the heating coil, it starts to heat up, and we can see how the heating coil affects the water temperature as it goes up. Let's go upwards. All right. Now, this is the other image that I want you guys to send me. So we have so far we have 1, 2, 3, 4, 5 images, all right? We have the residual image and the electromagnetism image from the CFX solver. We have the two heating coil sides images, and we have this ring image right here, okay? But for a better quantitative analysis, we can actually create a chart of the temperature distribution, all right? And how we're gonna do this? First, we will create a line, all right? So go to location, line, you can leave the name line 1, and the line will be set to the first point, minus 0.7500, and minus 0.7502 2.25, and we want 200 samples from this line, okay? And you can see that the line is set to be right there between the heating coil and the water domain, okay? So there is our line, and this is where we will extract the temperature value. So let's create a chart for this. This is the first time that we use a chart. So this is another tool that I'm presenting you guys. So create a chart. You can leave, no, let's leave it a valid name. Let's say that this is the temperature profile. Okay, you can leave this here. In the data series, we'll select the line that we have just created, and the y-axis we're gonna use the temperature, okay? And you can apply. And this is the distribution of temperature along the line, okay? So I want you guys to send me the values for this. How you do this? You go to export, and you're going to export this CSV file, which is a file that the Microsoft Excel, for example, can read. So you can name this whatever. I'm going to name it temp prof, which is temperature profile, and you can actually see this in Excel. So we're gonna have something like this. All right, we will have the temperature distribution right there. To better see this, you can do something like this. Let's open this with the notepad. I actually did something that I did not want to do there, which is open the every time I open this file like this is, but I can change this later, okay? Now let's open Excel. Let's open this file that I just created. Here, heating coil, and let's open this one. Okay, it's open the same way. Oh yeah, I'm using the CFD 2010 Excel, right? It's not the newest one. That's why I open it here. But what I would want you guys to do, if you have a newer version of Excel, it will pop an image, a window here, and there's gonna be an option there that's gonna say, okay, you want to delimit this using what? And you're going to use separated by commas, all right? But basically, I want you guys to do this same graph in the Excel using this data right here, okay? So we're gonna have a graph that is very similar to this one. We'll have the x-axis. This is going to be the x-axis, and this is going to be the y-axis. And you're gonna send me, you're gonna create scattered data, a scatter graph with smooth lines and markers, and you're going to send me this data right here, okay? Which is we're going to send me the Excel file of the graph, but your graph I expect to look something like this, okay? So basically, this is what you guys to do, right? So we'll have 5 things to send me, right? You have 2 images from Solver, which is the residual target image and the magnetism image. You have the 2 images from the sides of the heating coils. You have the ring image, and you will send me this Excel file with the chart, okay? So I hope you guys enjoyed this problem. We introduced electromagnetism, which is something that a lot of engineers can use, and I think it's a very interesting problem, okay? Remember, this could be used not only for heating but for cooling systems as well, okay? So I hope you guys enjoyed this lecture, and I'll see you guys next week. Just as an addendum, if you have an older Excel version, what you can do is you go to the temp.prof CSV file, you go to rename it, and you change the extension. From CSV, change it to the text extension, TXT, okay? And you can click, say, yes, I want to change this expression. Now you can do something like this, right? Click it, go to open with, choose another software, and you can select, well, because it's not here, I'm going to do it different. I'm going to open Excel, and I'm going to open this file, okay? All files, and this is the window that you will have pop up, so you can delimit it, okay? Click next, and you can see if I select comma, because the data is comma delimited, as you can see right here. If I select it, it will separate it by columns, all right? So now I can create the graph way easier, all right? So I go to insert, scatter with lines, and then we're gonna have something like this. Right click it, select data, and the X1 is gonna be the first column, and the Y column will be the second one. There we go. We have 200 points of data right here, but I want this graph to be a little bit prettier from you guys, so I want you guys to send me something like this, okay? Temperature, profile, which is something that you will need to do if you are preparing graph data for your client or for your paper, for example, okay? And this was in Kelvin, and this is the X. This is the Y direction, actually, right? Because it's going upwards, okay? Actually, it's the Z direction, sorry, because it is a line, okay? It's a line that was going through here, so this is the Z direction. Or you can even put, let's put it better, let's put it like height, okay? So this is the file that I want you guys to send me, okay? With the data right here and with the graph, right? Now, see you guys next week.